Hello, I'm Paul Francis from Aurora Consulting in the UK. Today, I want to walk you through some interesting and what perhaps might be surprising to some findings and conclusions that emerged during a recent project we've been involved in. Let's get started. What I'd like to consider is two different approaches to the modelling of a particular problem, what I'll refer to as a state-centric approach and a data-centric approach. I should mention right from the start, though, that both modelling approaches, of course, required an understanding of the information to be managed using class models and the state-dependent behaviour within the system defined using one or more state models. The application I'll be describing is the digital twin of what I'll refer to as the protocol processor. The same modelling formalism, Shlaer-Mellor, was used in both approaches, and the executables for each was generated by the same model compiler. As we progress through the presentation, I'll endeavour to highlight the pros and cons of each modelling approach, briefly touch on what we observed in respect of their runtime performances, and then finish with a few conclusions. Okay, let's look at the problem space we were looking to model. As shown in the slide, the purpose of the protocol processor is to process transactions, of which there could be many different types, according to a specific protocol, i.e. a series of steps that might include transmissions and acknowledgements, consistency and security checks, step sequence checks, authorizations to share, etc. The protocol should be expected to be different for each transaction type. Each example transaction types might include financial credits and debits, messaging, trading exchanges, etc. In order that the behavior of the protocol processor can be verified at runtime, it's required to generate auditable events or messages, and these are monitored by the digital twin, our project in this case, and used to check for the correct behavior and various failure modes of the protocol processor, i.e. it provides an additional independent security guarantee that the protocol processor is behaving as required. Okay, that's a brief tour of the problem space. Now let's look at how the behavior verification requirements of the digital twin were modelled. Two different modelling approaches were considered, a state-centric approach, and this is where we initially started. After all, it felt like a state machine problem. In this approach, the protocol rules for a given transaction type were captured within the state model, with the transitions between the states defining the expected sequences of the steps for that protocol. However, it soon became obvious, for reasons that will become clearer, that a different approach would be required. Which brings us to the data-centric approach, where the protocol rules are instead captured in data, as defined in a class model, and the expected sequence of steps for a protocol are now defined as instances of the classes and relationships in that model. Both approaches were implemented, one model for each, with the executable code being generated by the same model compiler and the characteristics of the two solutions compared and contrasted. Being able to develop and contrast two solutions in parallel is perhaps a rare opportunity, but it provided some valuable insights, which we will go into in a few moments. It should also be noted that this dual approach was greatly accelerated by using an executable modelling formalism, Shlaer-Mellor in this case, supported by a code generation and regression testing environment. As you can see, the class model for the state-centric approach is relatively simple, all of the protocol rules being managed within distinct state models, one for each type of job or transaction type. In fact, the model could potentially be made even simpler. The subtypes declared through R1 were included in order to separate the instance population of jobs currently in progress, the active jobs in this model, such that any find process operating over those instances would always return within a tolerable time, no matter how many jobs have been processed. This part of the model turned out to be unnecessary, because the completed jobs were always deleted after a very short period anyway, resulting in the number of current job instances always being kept relatively small. Nevertheless, this model fragment is a pattern that could be used in either of the two approaches, should it be necessary. The need to model each type of job as a separate subtype, however, means that the model is extremely brittle to changes and additions to the types of jobs supported, with a new subtype needing to be added for each new type of job. Let's now have a look at a state model for one of the job types. As you can see from its shape, the state model clearly reveals the sequence of steps that the respective transaction goes through, with the pink states representing the expected behavior, the turquoise states representing failure conditions, and the grey states representing locations in the sequence where alternative paths might be taken. The additional brittleness that the state-centric approach suffers from, however, is that changes to the protocol necessitate a change to the state model, which typically results in downtime whilst this change is rolled out. So let's quickly summarize the pros and cons of this approach. As we saw from the previous slide, the steps in the respective protocol are easily understood from the shape of the model itself, and simple sequences are readily supported, which can include simple branches. However, more complex sequence topologies are much more difficult, especially when you consider that the order in which events from different branches might arrive is unpredictable, resulting in many additional states and transitions needed to support this, and the state model no longer being able to readily reveal the steps in the sequence. Further, any change to the protocol requires a modification to the state model. And finally, each new type of job will require an additional subtype of job together with its own prescriptive state model. Let's now have a look at the data-centric approach to the same problem. Let's explore the key features of the class model that supports the data-centric approach. There are two key regions to this model. The yellow classes, the specification classes, capture the protocol rules. The classes and the relationships between them define the legal event types and the order in which they appear in protocol sequences, and which sequences are applicable to which types of job. The model supports a variety of complex event sequence topologies, including branching with parallel threads and multiple endpoints, merging, multiple start points as illustrated here. In the example shown, each dot represents a particular event type that is expected at a particular point in the sequence, and is abstracted in the model as an instance of the class named AE occurrence in sequence definition. The white classes represent the actual jobs, sequences, and events that can be determined from the event stream provided by the protocol processor. Note that the only limiting factor of this model are the required properties of the event sequences, i.e. the variety of different event topologies that are supported. To date, all of the known event sequence topologies can be supported without changing the model, with protocol variations supported entirely by reconfiguring the instance populations in that model. And here's the state model for a job. It works for all types of job. It is applicable for all job types because its role is simply to verify that the protocol rules for a given job type are being adhered to. And it does this by progressing through a series of states that check different aspects of those rules, which are themselves defined by the class model, not the state model. The key point to bring out here is that both the class model and the state model are independent of any type of job, and therefore the model as a whole is significantly less vulnerable to changes in protocol and/or job type variations. Let's quickly summarize the pros and cons of this approach. Firstly, the approach scales to any complexity of topology. The model would handle any of these topologies, for example, using different instance populations of the same model. Changes to an existing protocol sequence simply requires reconfiguration of the model. And other applications and job types are also readily supported without a model change, provided they are within the limits of the supported topology types. The one possible downside is that none of the models provide a human-readable visualization of the protocol sequence, but alternative ways of declaring the protocol sequence could be used, with tools based upon sequence diagrams being used to declare the different protocols, the output of which can be processed and used to configure the instance population of a digital twin. The data-centric variant of the digital twin application is provided with two interfaces. A configuration interface that provides a means for configuring the protocol rules by populating the specification classes and relationships, and a protocol verification interface that consumes the audit event stream and invokes the checks that test if the protocol processor is behaving correctly. In order to provide a user-friendly way of defining the protocol definitions needed by the digital twin, a tool chain was devised that used a plant UML-based specification for defining the protocol specifications in the form of sequence diagrams, and a translation engine, the plus processor, whose job it was to convert the sequence diagrams into event definitions of a form consumable by the configuration interface. Without this, the job of configuring the protocol specifications within the digital twin would be a moderately skilled job, with users needing to have a thorough understanding of the model in order to configure it appropriately for the protocols of concern. The toolchain thus provided an effective means to overcome perhaps the single criticism of the data-centric solution, and resulted in reducing the skill level needed to configure the digital twin from a niche level to that of a commodity level, and focusing the problem on the subject matter rather than the technology needed to support it. Additionally, to support testing, an event simulator was also developed to generate example event sequences at a scale similar to that of the protocol processor. The runtime performance of the generated executables for the state-centric and data-centric models were compared. Our expectation was that the state-centric approach would be significantly better than that of the data-centric approach, but this turned out not to be the case for even the simplest topologies. So, in conclusion, the two approaches had a very similar runtime performance, though increased topology complexity is likely to favour the data-centric approach. The state-centric approach was highly brittle in the face of changes to the protocol rules, resulting in the need to modify the state models and rebuilding the application each time. Whereas the flexibility of the data-centric approach required only a reconfiguration of the model to achieve this, which could in fact be done at runtime. And the approach also more readily supports a range of applications beyond that of the application of the protocol processor. Finally, the provision of tools to specify the expected event sequences and a translation to generate the event definitions required to configure the digital twin resulted in a highly effective, user-friendly means for specifying and visualizing the protocol definitions. It shouldn't be a surprise to anyone that ongoing development of the digital twin is now solely focused on extending and refining the data-centric model. Thank you.